As one of only few mathematicians, John Nash won the Nobel Prize in Economics for his remarkable work in the field of game theory. The 26 pages long PhD thesis of John Nash counts as one of the most influential papers in economics. This paper always struck me because it was so short, and as an undergraduate I wanted to understand why it was so influential. In the paper, Nash discussed the domain of non-cooperative games. It turns out that these games are quite common and useful in our daily life, and especially in analyzing competition scenarios in economics. Today, we're going to discuss the first basic concept used in this paper, Nash Equilibria in pure strategies. The Tale of Two Fishers. Consider two fishermen who live their lives in Great Britain, fishing just enough to live a comfortable life, but the fishing activity of one never really affects the life of the second one. They never met. They can decide whether to fish much or to fish less, which is a binary choice. The payoff they get, in this example the amount of fish, is dependent on their decision. The decision of the first one is not important for the decision of the second one. This basic decision can be conceptualized in a payoff matrix. Chapter 2. Payoff structure of simultaneous games. We conceptualize the situation in a payoff matrix. One small assumption we make here is that both fishers decide on Monday morning at the same time how much fish they need for the week. Now you see a matrix. On the left side you can see the alternatives the first fisher can choose from. In the first row you see the alternatives the second fisher can choose from. In this setup, both fishers have the same basic decision to make. Do I fish less or do I fish much? They either decide to fish less or to fish much, but no combination of both strategies. These are called pure strategies, and they are one of two possibilities. Players in game theoretical terms can have a pure strategy or a mixed strategy. For now, we will concentrate on pure strategies. A pure strategy is defined by only one strategic choice, depending on the strategic choice of the other players. In the cells, you can see the amount of fish, in more general, the payoff of the fishers. In each cell are two numbers. The left number is the payoff for the first fisher. The right number is the payoff for the second fisher. The payoffs of the fisher could depend on the decision of the opposite fisher, but in this basic setup they do not. Now fisher 1 thinks about what to do, given the assumption that fisher 2 fishes less. Since the amount of fish when he fishes much is more than the amount of fish he gets when he fishes less, he obviously chooses to fish much. Exactly the same thinking has the second fisher. It does not matter what the opposite fisher chooses. It is always better to choose the strategy much fishing. Here we have a situation in which one strategy is strictly dominated by the other one. In game theoretical terms, this just means that one could theoretically exclude the strategy from the thought process, because it is never chosen. Since less fishing is strictly dominated and therefore both choose to fish much, we end up in an equilibrium where both fishers choose to fish much, regardless of the opposite. This is called a Nash equilibrium in pure strategies and is defined as a point in which both individuals do not have an incentive to deviate from their respective strategies. In this scenario, no fisher would choose less fishing, given the other fisher chooses much fishing. Later this concept will be important as well. A small remark at this point. With no externalities, the Nash equilibrium we find is the Pareto optimal point as well, the point with the highest sum of payoffs. Chapter 3. Introducing a new technology. To initiate a situation that illustrates a non-optimal Nash equilibrium, let's consider a new development. The fishers in Old Britain are getting new technologies to fish, enabling them to fish much more. This is good, isn't it? The problem with this new technology is that it makes it possible for one fisher to fish that much that it really affects the other fisher's ability to fish. This is called a negative externality. This, of course, results in a new situation and a new payoff matrix. Chapter 4. What has changed? Okay, let's compare the two payoff matrices. The new technology enables both fishers to gain more fish in less time. They could both fish less and earn the same payoff as before, playing with their children and spending quality time with their wives in the spare time. But if one of both deviates from fishing less, he could earn an even bigger amount of fish as a consequence. But here's the catch. There is not enough fish for both fishers to both fish much. If one of both fishes much, he skims fish off the territory of the other fisher, resulting in a reduced amount of total fish in the sea, subsequently reducing the amount of fish for the opposite fisher. But it gets worse. If both fishers decide to fish much with the new equipment, they reduce the total amount of fish that much that they are both worse off compared to the situation where they did not have this crazy new technology. But now you could rightfully think, but then they just won't fish much, instead fishing less, earning the same amount of fish with less work. But this is not what is going to happen. Let's analyze this new payoff matrix. Chapter 5. Solving the new game. Okay, we have described the new game, but are there any Nash Equilibria we can find? Let's start by assuming that the second fisher chooses to fish less. What should the first fisher do? He compares his amounts of fish and obviously chooses to fish much. But what if we would have assumed that the second fisher fishes much? Then the first fisher decides to fish much as well, as he compares 0.5 and 1. Again, less fishing is strictly dominated in pure strategies, and the first fisher will always choose to fish much. Now let's look at what the second fisher would do, assuming he knows that the first fisher always chooses to fish much. He compares 0.5 with 1 and decides as well to fish much. This is a Nash equilibrium as well. None of them both can individually better his situation by choosing to fish less instead of fishing much, assuming that the opposite is fishing much. They have to coordinate themselves in order to create a better situation for them both. Conclusion. Paradoxically, the optimal behavior of both fishers individually leads to a situation in which both of them are worse off than before. They could both be better off if they just would have fished less. But individually, then they both would have an incentive to deviate from the status quo. We analyze the situation of a simultaneous, non-cooperative game with full information on both sides. The techniques used to find Nash equilibria are pure strategies and strict domination. This is just one example. In order to get better with these techniques, one has to analyze many games with more players and unique situations. Now you may ask, why is this such a groundbreaking idea? Analyzing non-cooperative games. Because non-cooperative games are everywhere. From the prize-making behavior of firms, to the work in teams of big corporations, to how students in class interact with each other in order to maximize their grades. Even in poker games, we observe non-cooperative games behaviors. This is just an introduction into the big realm of game theory, discussing the first main idea. Thinking about non-cooperative games is thinking about decisions in our daily life. Many thanks for your attention and have a good day.